We'll see. Hopefully that works this time. So linear data, if you were to graph it, would look like this. Straight line pattern. You could also have a downward straight line pattern like that. Right? That still counts as linear data as long as it makes a straight line when you connect the dots. Non-linear data could look like anything that's not a straight line. Typically, we see things like this. Right? It curves down, then it curves up. Or it curves up, then it curves down. But it's also possible to get all kinds of crazy things. You get something like this. That's not linear, right? Because there's a curve to it. Even though it never was going down, it's curving, so it doesn't count as linear. Or something like this. And it's like gets a wave to it. Those things would be called nonlinear data. Discrete data. So we've also talked early, like really early in the video, we talked about something called discrete data and something called continuous data. Discrete data is something that has like jumps to it. So when you're measuring discrete data, I like to think of shoe size as discrete data. So for instance, if I said, what's your shoe size? Everybody would have, like, I'm a size 7 or 7.5 or 8 or 8.5, and it jumps up by half sizes. Nobody in here is a 8.23. And nobody's got that in-between size. That's discrete data because it jumps from one thing to the next. Continuous data is the opposite of that. It is something that has connections all the way through it. For your continuous data, I like to use temperature as a good example because the temperature outside, it doesn't go from -10 to +5. It doesn't just jump, right? It slowly gets warmer, slowly gets colder, and it makes nice continuous data. It goes from -10 to -9.9 to -9.8 to -9.7, and it gradually gets to where it's going. It doesn't have jumps. Discrete data, when you graph it, looks like this. There's gaps in the data, right? So it goes from point to point to point to point. Continuous data is what we've done a lot of work with. Continuous data creates straight lines like that. Everything's connected. Some examples of discrete data and continuous data. I've already given you a couple. This is a three different types of discrete data. Four different examples. So the first one's the bullet point. It's in words right here. So the cost of attending a concert related to the number of tickets purchased. That's discrete data. So if you pretend that it costs $100 to go to a concert, if you buy one ticket, how much is it going to cost? It's going to cost $100 for one ticket. If you buy 2 tickets, how much is it going to cost? It's going to cost $200. If you buy 3 tickets, it's going to be $300. And you notice that you're jumping from one to the next, right? At no point did I pay $102 or $103 or $104 or $105. Right? I just jumped from 100 to 200. That's discrete data because it jumps. Another example of discrete data would be the number of fishing boats anchored at an inlet. In an inlet. So we're looking at this graph right here. That's discrete data for a couple reasons. One, because when I look at the graph, the lines aren't connected. See how the dots aren't making a nice line? Well, sorry, they're making a pattern, but there's no line connecting them. Right? So that means this is just discrete data. This point right here tells me that at 9 a.m., there was 25 boats. And that's what that point tells me. So the X value is 9 a.m. Boats is 25, approximately. And then the next piece of data jumps to right here. That would be 10 a.m. and now it's jumped to 10 boats. Now, in between, there is no data. We could definitely assume that all, 15 boats didn't just leave all at once. But even if we imagined all the points in between, there would still be jumps in there. It went from 25 boats to 24 boats to 23 boats to 22 boats. At no point was it at 23 and a half boats. And it's not possible. So it's not continuous. It's still jumping boat by boat by boat by boat. In this case, it jumped by 1 hour, and then the measure of boats in between. If we look at the graph to the right, we'll look at another graph. That's the cost of publishing a yearbook. So if you look at this, it looks to me like you can only order yearbooks in 50s. Because if you look at every single block, it goes from 50, then it jumps to 100, then it jumps to 150, then it jumps to 200. So my guess is that you can only order them in 50s. So since you can only order them in 50s, that would be discrete data because it's jumping up in your orders. You never ordered 51 or 52 or 53 or 54 or anything in between. Yeah, 51.5, right? You couldn't order that. 56 and a half, 56.9. Like there's little spots in between that don't exist. The last one is this table of values right here. So if we look at it, the X values or the independent is the number of bottles of pop purchased, and then the cost is on the right. And again, you'll notice the jumps in the data. So I go from 1 pop to 2 pop to 3 pop to 4 pop, right? I'm jumping up. There's nothing in between. I can't go to a store and buy one and then a little bit of a pop. I have to make that whole jump up. And because I'm doing that whole jump up, it's then causing me to have entire jumps in my Y's as well. That's discrete data. It jumps. Yeah.
So can something be like linear, like continuous?
Can something be continuous?
And like linear.
Oh, yeah. So linear and nonlinear, if you look at these patterns right here, some of these are linear, some of these are nonlinear. So if you look at the boat one, that does not make a linear pattern. This boat one looks like it makes kind of one of those like swoop things. Right? Where it's got like a big turn in it. This one looks like it's a linear pattern. Even though we don't connect it with dots, it's still a linear pattern. This one's not linear. And then with continuous, the same rules apply. So you could have a nonlinear or you could have a linear with the dots connected. We'll look at some continuous data. So the one in words, the distance that a car skids when the brakes are activated is related to the initial speed. That one's kind of a complex one. This one right here. The faster you're going, the further you're going to skid. Right? Like that's kind of the rule of thumb. And it is possible that you're traveling a little bit faster. So you could be going 100 kilometers, or you could be going 100.1 kilometers an hour, 100.2 kilometers an hour. You could be going that like little bit faster. And if you went that little bit faster, you would skid that little bit further. So that would be continuous data because there is moments in between. When I'm driving my car, it doesn't just go from 0 to 100, although it'd be pretty sweet if it did. Right? It slowly gets up to that point.
Yeah. Well, couldn't the like how far the car skids be also related to how good the brakes are?
Yeah, definitely. Or like how good the tires are, or how icy it is before the telephone pole in front of H.J. Cody, or all other kinds of factors in there.
Would weight also sort of come into a factor because
Yeah, so like someone's like a semi truck needs more braking room, right? So if it's going 100 kilometers an hour, I'm going 100 kilometers an hour, it needs way more braking space than I do. But it would still all be related to each individual vehicle, that the relation of distance and speed, right, would be continuous.
what even happened with that whole?
I don't know.
Did someone hit it?
Yeah,
Oh.
crash your car into it. Must have been good. I don't know. She's okay. That's what matters. All right, another one. Temperature, almost anything to do with temperature is probably going to be continuous. We're also going to talk about altitude. Does anybody know what altitude is? Yeah, it's the height of something. We usually talk about altitude with planes, right? The height of a plane, the altitude that it's flying at. If you have the height of this thing, it doesn't say what it is. We're gonna pretend it's a plane because I don't know many things that are going that high. Um, when you're talking about the altitude of a plane, it doesn't just jump from 610 meters to 1,220 meters, right? The plane's not just flying and then all of a sudden it's right here. It flew up and it gradually got there. That means there's continuous information in between. There has to be. Same with the temperature. The temperature doesn't just jump from 15 degrees to 11 degrees. It had to have gradually changed in there somewhere. It like cooled off or it heated up, one or the other, but it gradually happens. That's continuous data. When you're looking at a graph, these two examples, one's linear, one's nonlinear, both are continuous because they've connected the dots for us. So when I see a straight line like that, that tells me for sure that's continuous data. If you read it, it also makes sense that it's continuous data. So the top one is the height of a plane at a given time. And you'll see that's the path of the plane. It's slowly going down. So the plane started here, and the plane slowly is going down. The longer it takes, it's lower and lower. It doesn't just jump to a spot. That'd be terrifying. The height of a tide, so that's like the height of the water in the ocean. And it doesn't just automatically lift or automatically drop. It slowly lifts all day, and then it slowly goes back down at night. That would be the height of your tide. It goes up and back down. Tide comes in, and then tide goes out. It's all continuous. Awesome. Variations. I don't use these words very often, so I'm going to talk about them real quick. We have a direct variation or a partial variation. It just kind of has to do with where you started. So if you look at the graph on the right, the blue one is our partial and the red one is our direct. And it has to do with passing through the origin, where your y-intercept is. If your y-intercept is at 0, which is the origin right here, then we call that a direct variation. Because it started at 0, and then the only thing affecting it is the independent variable, the input. The partial one has a different y-intercept. It could be anywhere as long as it's not the origin. We call that a partial variation. Again, you're probably never going to hear me use those words again. The only thing I like to refer to is the start point. Right? Does it have a different start point than 0? And if it does, then what is that start point? Like what we practiced yesterday. Okay, now the biggest thing we're probably going to do today, interpolating and extrapolating information. So these both mean using the data, and the data could be table of values, the data could be an equation, the data could be a graph, just the data of some sort, to make predictions. So they both mean that. One of them means that you're making a prediction, and that prediction falls within the boundaries of what you already know going on. And one of them means you're making a prediction beyond what you think is going on. If we looked at a graph, for instance, let's look at this graph. We're going to look at this boat graph. If I was to look back at this boat graph, and I asked you to predict how many boats were in the water at 9:30. 9:30 happens right here. My guess, looking at this pattern, it would probably be like somewhere in there. That's my guess of where that dot would be. Based on, it looks like it's making a curve. Right? So there should be somewhat less than that and somewhat more than that at 9:30. So I'm guessing, and I'm not right or wrong, I'm just guessing it's somewhere in there. If you put a dot a little higher than me, that's fine. If you put a dot a little lower than me, that's fine. We're just guessing. We're predicting. That would be interpolating data because my point is in between other points I already know. And if I look at this, I'm like, okay, I have a point on the left, I have a point on the right. I'm in between the data given. That's interpolating. If I was to say, predict the time or the number of boats at 5 o'clock, I would say, I don't know, maybe it's like this. That would be extrapolating data because I'm outside of the points I already know. I have a point to the left of it, but then there's nothing else. So I'm outside of the given information. That's extrapolating. The way that I remember which one's which, I like to think of interpolating as inside, in and in, and then extrapolating as exiting. So I've exited the data, I'm beyond it. That's my trick of knowing which one's which. Both are just ways of predicting information. Silence. Scared. All right, let's try a question. Example 1. We have a nice little graph on the right. It's telling us the distance that a car is driven after a certain number of hours. It says use the graph to estimate the distance traveled in 1.5 hours. So if I wanted to use this to predict how far the car has gone at 1.5 hours, I need to figure out where 1.5 is on my hours axis. Hours is my x-axis. This is 1.5, my blue line. We agree? Like that would be 1.5 on my x-axis, right? Halfway between 1 and 2. Now I want to figure out where on my line it's at 1.5. To do that, you're basically just going to go straight up until you hit the line and you find a dot. That is the moment in time where your car has traveled 1.5 hours. That blue dot, that's where your x value is 1.5 hours. You now have to figure out what the y value is at that point, and that will tell you how far you've traveled. If you look, the y value is, I'm going to guesstimate about 125, right? The reason I'm guessing 125 is because this, the green dot, is halfway in between 200 and 100. So that's probably 150. And now I'm trying to find halfway in between 150 and 100. That's how I got 125. So my prediction using this data is that it will have traveled 125 kilometers in 1.5 hours. That would be an example of interpolating. I've used my information to make a prediction that's within my boundary. Right? I haven't gone beyond my line yet. I haven't even gone beyond my points. That's the main thing. All right, we could do this in reverse. So I could say, how long does it take if you've gone this far, which is what the second bullet point says. It says, estimate the time to go 300 kilometers. To do that, you look at your y-axis this time, and you find 300 kilometers. Looking at my y-axis, this is 300 kilometers. That nice green line that I just drew. That's 300 kilometers. I then go straight right until I hit my graph. And that will tell you where on your line you have 300 kilometers. Then you use that point to figure out what the time is. My prediction, 3.75. So my guess is right here is 3.5 because that's perfectly halfway. And I'm in between 3.5 and 4. If you said 3.7 or 3.8, like that would be good enough too. I'm going to go with 3.75 because it's like nice and round. It's halfway. So I'm going to say it takes 3.75 hours. Which is 3.75 hours. Again, that would be interpolating because that point that I just used to predict is within the points they gave. It is inside of them. Okay, we're going to try another one. So this one has no words given to it. It just has a bunch of values and a line. We're going to use that line to find values. The first thing we're going to do is find where on that line x equals -3. To figure out where x is -3 on this line, I go to my x-axis and I find where -3 is. So that green line I just drew. That's -3 for x. Agreed. That's x equals -3. Perfect. Now you're looking for a y value. So you need to figure out how far up you have to go until you get to your line. So I have to go up to right there. That has an x value of -3, a y value of +3. So when x equals -3, y equals +3. Sorry. We'll try again with x equals 6. So if x equals 6, which is the next point that we have here, I'll do it in blue. If we have x equals 6, on my x-axis, I have to find where 6 is. It's out here, my blue line. Now I have to figure out my y value, which is how far up or how far down I have to go to get to my line. In this case, I have to go down to get to my line. I have to go to right there. That point would approximately be at 6, -1.5. It's past -1, but it's not at -2. So I'm just going to say it's in the middle. I'm going to say -1.5. Using a graph like that is much faster than when we used to put the inputs in and then make calculations, right? That's a slow process. If you have the data or the graph, it's a quick way to just look and check, especially when you get good at it. You could do it the other way too. So they could give you an output or a y value, and you could look for your input, your x value. Let me do this one in purple. So now they've said y equals 4. So that means somewhere on your graph, you're going to look for y equals 4. It's right here, that purple line. This time, instead of going up or down, you're going to go left or right because you're looking for an x value. And x values go left or right. So this time, I'm going to go to the left until I hit my line. And I hit my line right there. That point is at -5, 4, which means my x value is -5. Okay, I want you to try to find where y equals -2 on your graph. Okay, so on this line, what's the x value when y equals -2? All right, if we try y equals -2. I'm going to do it in orange. I'm going to zoom in a little bit so you can see maybe a little better. I'm looking for y equals -2. On my y-axis, this is -2. I then have to figure out how far left or right I went to get to my line. In this case, I have to go to the right. My x value is on that spot. That's going to be 7, comma, -2. So when y equals -2, x equals 7. Yes, sir. Inputs go kind of fast when you do them algebraically. Outputs are slow, right? Remember when I gave you equations and I said y equals? You had to do all that moving of numbers, and it was a big pain. If you have a graph and given an output, it's easy to find the input. And those last two are quick. You find where the y value is, you move left or right, you got your answer. Much easier than doing the big equations. All right, here's a bit of a word problem. Again, we're going to try to interpret our graph. So it says this graph shows the cost of running a backhoe related to the time it is working. You look at your graph, it's a nice straight line. It's a linear equation. Question A, what is the cost to run the backhoe for 7 hours? They told me I was running for 7 hours. So that means on my graph, I'm looking for 7 hours. On my x-axis, that's 7 hours. My purple line I just drew. I'm trying to zoom in for you, but it won't let me. And because I'm looking for a y value, I need to go up. When I go up, I get this moment right there on my line. And then I'm going to make a prediction about how much it costs to run it for 7 hours. My guess, looking at this, that should be 500. And we're about halfway in between 600 and 500. So I'm going to say 550. It looks like it actually might be a little bit higher. So if you put like 570 or something like that, that'd probably be fine too. But you're just going to go anywhere in that spot. So I'm going to go 550. Okay, try B and then see if you can remember how to answer C. So remember we talked about direct and partial, so you're going to look at your notes. How many hours is the backhoe run when it costs $350? So this time, gentlemen, boys, thank you. So this time they gave you a y value because they gave you a cost. So that means you're looking on your graph for where 350 is. 350 is approximately there, right? It's not actually on a line, so it's in between the line and 200. And then you need to go straight right to this point. And I would say that is run for 3 hours. Is this relation direct or partial? Direct, X and Y. It's a straight line, truth.
And it's like not like outside.
Yeah, it's not off, it's not outside of this point right here. So you notice that the y-intercept is 0. If the y-intercept is 0, then you have a direct relation. Right? That's what you're looking for. Yes, sir.
You measured it like 250.
Oh, good save, man. It should have been here. 350. Which is here. Which is 4 hours. Good save. One time, I made a mistake on a video, and then I got chirped on YouTube by some guy named like Ahmed. He's like, "Hey man, you made a mistake at 2052. You shouldn't even be a teacher." I was like, "Whoa!" Like, no, shots fired for no reason from some stranger. So we got in a YouTube fight over it, and I kept arguing with him. It's how we started every class. It was me arguing with Ahmed. It's nice. Okay, we have another graph here. This one's showing the cost of something compared to the number of sweatshirts that you've bought. About how many sweatshirts can be bought for $700. They gave you a price, so you need to find that price on your graph. 700 is right there. Because you found a y value, you now are moving left or right to get to an x value. I'm moving to the right to this point right there. That point is approximately there, which I would say is 35. Right? 30 would be halfway in between 20 and 40, and I'm halfway in between that 30 and 40 marker. Yeah, so as long as it's reasonable. So on this question, 30 wouldn't do it. So if we're looking at this, what a reasonable answer would be is if I look, 700 is dead on that graph. Like it's perfectly on this line. So that means you can follow, don't do that to my desks. So if I follow that line, I notice it hits right there, which is definitely past the other grid point. And that grid point is exactly 30. So my answer has to be in between 30 and 40. Now, if you guessed 31, that might be a little rough. 32, I'd probably give it to you. So 32, 33, 34, 35, 36, 37, 38, I'd probably accept all of those. 31 and 39, I don't know. You're not really that close to either of those lines, so I probably wouldn't give it to you. But that's what I mean by a reasonable guess. As long as you're within a range, I'm pretty much happy. And the range I'm looking for is in between 30 and 40 on that one. Yeah, right? Like it just has to be close enough. Does that make sense? Because there is no like perfect answer. Sometimes there is. I shouldn't say there's no perfect answer. Some of them are perfect, right? Like if you look, this point right here, that's perfectly at 20 and 500. That's perfect. Stop. Joey, don't. Thank you. And it's perfect in that spot. B, what is the cost of owning 15 sweatshirts? I'm now looking for 15, approximately 15 on my x-axis. I would say this is 10, so 15 would be halfway in between. If I go straight up from there, you get that marker. That's one that's hard to predict. Right? Like it's past 400, but it's not really halfway past 400. So that would be a hard one to make a good prediction on. If I was looking for an answer, I know that this spot is 500. So I'm looking for somewhere in there. I would probably want to be below 450, but above 400. So I'd probably accept, 425, 420, 415. I'd probably even take 430, 435, anything in there. As long as you're below 450, above 400, I'd probably accept it.
So like if you like 420 or 430, not okay.
That'd be okay.
Oh.
Yep. Like I would accept a wide range of answers on those ones. C, what is the initial cost to set up your order? So initial cost means that you have bought 0 sweaters. If you've bought 0 sweaters, you are at that moment in time and you're going straight up from there. You hit that point. That's also known as your y-intercept. So your initial cost is your y-intercept. Right? I call it my starting value a lot of the time, my start cost. It'd be $200. My guess is that it's you probably designed a sweater. So for instance, when we know we're gonna buy grad hoodies or something, they're gonna charge us money before we've even ordered any hoodies, just to design it and set it all up. And then every hoodie you buy costs a different price. Is this direct or partial? This is partial. The reason it's partial is because it has a y-intercept that's not 0. Y-intercept isn't 0. Awesome. Example 5. I want you to try this on your own. So see if you can interpret that graph. Just do part A and B. You can wait for C. So what was the length of time it took for the dog sled race to finish? It would have finished at the end of the line I got here, right there. Right, that's the distance to the finish. It's at 0. That means that's when it finished. It took 2.5 hours. How long was the dog sled race? Well, the length of it would be however far away you were at the start, which would be right there in green. That'd be 60 kilometers. The average speed. So some people were saying like the average speed's the middle. Yeah, it's a linear equation, so that kind of works out. The way that you do average speed for this is you would take however far you went. So in this case, we went 60 kilometers. And you would divide it by however long it took you to travel that distance. So divide by 2.5. Yeah, so you're taking your total distance, dividing by your total time, and that'll tell you the average pace you were going, which would be 24 kilometers an hour. 24 spot on. Yeah, it is 24 spot on.
You did that in your head?
Yeah. Just gotta keep practicing. So if you want, boys, yeah, like you have to take enough high-level math courses. So most of your math teachers have math degrees typically. I don't have a math degree.
You don't have one?
No, I have an economics degree, like a social studies degree.
Really?
Yeah.
Wait, so you math grade?
And I'm just really good. If you look at number 8, this question doesn't give you a graph. It gives you a table of values. So it says the table of values represents the distance that Sophie cycles in relation to time, and they give you a bunch of points. Remember that those are ordered pairs. It's been a while since we've done that. That means that we can graph these things. So when we graph them, one of your things is going to be an input, one of them is going to be an output. If you have time, it's almost always a guarantee that that's your input, which means that's your x-axis. So I'm going to put time on my x-axis.
Wait, how can we skip the other two?
Because we don't got time for it. The other one is going to be my output, which is going to be my y-axis. In this case, it'd be distance. Distance. I'm writing a vertical because I got no space. Now you've got to choose like how far things are going to go. So for me, the way I like to do it is I try to figure out my lowest value, which is always usually 0. And then my highest value, in this case, I'm going to say my highest y value is 80, which is a bit past 75 because we want to go a bit past. And I'm going to say my highest x value is like, I don't know, 7 or 8. That way, if I need to go beyond my data, I can. And I might have to adjust that later. Come on. Right? So maybe 80 is too far, maybe 8's too far, and I'll adjust it if I need to. Come on. But it gives me a starting point. And then I can ask myself, okay, what should I count by to get to 80? If I'm looking at this, I would probably count by 5s if possible or 10s. So looking at that, if you tried to count by 5s, It'd be 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. I don't have enough markers to count by 10s or 5s. So that tells me 5s doesn't work. And I try again, but this time with 10s. So I'm going to go, that's 10, 20, 30, 40, 50, 60, 70, 80, 90. And now the top one isn't 80, it's 100. But I use that as like a ballpark to start off my labeling. If I'm trying to get my hours out to 8, I might want to count by 0.5s, like half hours. If I did that, then this would be 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. Not enough. So going by half hours won't work. That means I'm going to have to count by hours. So this would be 1 hour, 2, 3, 4, 5, 6, 7, 8, 9. And now my maximum number of hours on my graph, instead of being 8, is 10. Try to use as much of your graph as you can. Right? That's the idea here. Don't make little tiny graphs. Try to space it out. We can now plot all these points. So remember, each x value is a y value, or has a y value. So like that is a pair. So when x equals 1, y is 12.5. I'm going to approximate it right there. That's a bad choice of color. Do not do green on a green graph. Right there. And that's just an approximation. When y or x is 2, y is 25. So I'm going to try to make that approximation right there. 3 would be 37.5, which would be about there. 4 is 50, which is there. 5 is 62.5, which is there. 6 is 75, which would be there. And you notice what we've created is linear data. So if I was to connect all the dots, I've made a nice straight line. With a graph, I can then interpret a graph really easily. That's the perk of it all. Right? So I took my data, turned my data into a graph. Now I can use my graph to answer questions about that data. The first question says, from the graph, determine the approximate distance she cycled after 2.5 hours. So I'm looking for 2.5 hours on my graph. For me, 2.5 was right about here. If I go straight up, that's 2.5. And I think it's safe to say that's really close to 30. Yeah, so if you said 30.25, 31, 29, anywhere around 30 would get you the mark. Especially since, I mean, some of those points are in between points, right? So you had to use a ruler to make a straight line, but everyone's line is going to be slightly different because we all made slightly different approximations. This is also why a ruler or a straight edge is very important, because it needs to be perfectly on that path. Question C. From the graph, approximate how long it takes to go 44 kilometers. 44 kilometers is approximately there. That means I'm going to come straight across to about there. And I'm going to guess it takes about 3.5 hours. Right? I'm just approximating. If you said 3.25 hours, 3.6 hours, that's fine.